So hello everyone, I'm very glad to welcome you all on today's demo day. Today's topic is quite exciting, if I say so myself. It says that we're going to discuss the evolution of programming languages, and I think it's going to be quite exciting. We will have a lot of questions and discussions as soon as Vlad is done. So let's welcome Vlad to start his presentation today. So I think you have the possibility to share your screen right now. So Vlad, can you share it?
Yes, hello, just a second.
Yep,
Trying to troubleshoot my Windows phone.
Cool. Yeah. And while Vlad is preparing, I would like to remind you that we can use the chat. The chat option you can use at any time. Just leave any of the questions over there. Or if you want, you can wait until we're done with the presentation and you will be able to ask any questions you would like at the end of it. But anyway, if you have a question which pops up while Vlad is presenting, please drop the question down below in the chat and we will discuss it as soon as he's done. All right, well, let's start the session. Vlad, please start.
Yes, hello everyone. Can you see me? Can you see my screen? This is how I look. I am a team lead at Crystal project here in Provectus, but I am not relevant to the presentation today, so I will just hide my camera just in case we need to save some traffic in the office, okay? So you can see the screen, right?
Yep.
Nice. So let's start the presentation. So during the small talks with the engineers, I discovered that many of us have some kind of understanding of functional programming concepts. We have our own ideas, right? And the ideas, they create kind of like this chaos, and it's quite difficult sometimes to understand and share them and to even like adopt new technologies in the project. Like when we are talking about functional paradigms, functional idioms, tools, functions themselves, what do they mean? What do we mean by that? Is Python functional? Is C functional? I can pass functions in C. Like side effects, monads, refresh and transparency, what are you talking about, man? Like we live in some kind of like chaotic info field, right? So I, by this presentation, wanted to some kind of arrange and organize the knowledge, right? So this presentation is just a high-level overview of how we got there. We will discuss the crisis which led to the creation of computability of different models of computation. We will see how computation evolved, how languages evolved, and then at the end, we'll just finish the presentation with some conclusion. That's the plan. Thanks, Morgan Freeman. Now, also, like, please take into account that in order to compress this huge philosophical and practical work into one presentation, it contains some kind of inaccuracies and discrepancies. So I guess that's the way I want you to encourage the thinking, right, and do your own research. So let's start digging into the story, so to say. So in the beginning of programming, the universe was created. It made a lot of people very, very angry. And then Georg Cantor created a set theory in 1870s. He decided to to group a number or collection of objects and apply some mathematical reason on top of it and call it a set. Then he used this set thingy, right, to discuss and research deeper into infinity. And he noticed that there are not one infinity, but in fact multiple types of infinities. For instance, number of real numbers within 0 and 1 is much bigger than natural numbers from 0 to infinity. Wow, cool, thank you, Georg Cantor. But the mathematics at that time was kind of turbulent. It was really a battle royale between different views on mathematics. So this made a lot of people angry because Georg Cantor, by his definition of set, created this turbulence again. And a lot of people disliked the notion of set and how it was delivered, right? So one group of mathematics like called formalists are very interesting for us. Why? Because they have the idea that mathematics is a language. In fact, we use mathematics to convey some kind of ideas, abstract ideas about number of things, ideas about calculation. And since it's a language, it needs to have some kind of strict set of rules, just like we have rules for English language, for instance. And by creating this set of rules for mathematics, they wanted to unify everything under one set of rules and axioms, so to say. Of course, there were different people like David Hilbert, who really liked the idea, and there were others who disliked it. Yes, that was the conflict, right? The crisis of foundation. David Hilbert was the leader of formalists, and he started researching into that topic. It was his passion to create one unified mathematics for everyone, to get rid of the problems. And one of the problems, namely, it's a self-reference paradox. It was discovered by Bertrand Russell, which kind of like defeated the whole set theory. So it wasn't like bulletproof, right? It also contained some kind of paradoxes. Namely, if the barber shaves everyone who does not shave himself, but no one else, who shaves the barber? Like if we have a set that contains sets that doesn't contain the self, then sets only contain itself when it doesn't contain itself. Like two descriptions of this self-reference paradox, right? And it really shows us how disturbed the mathematics was at that time. And of course, Hilbert was kind of like sad, yeah, if you can say so, but he didn't retreat. He was more enthusiastic to bring everything to order. Basically, it was just another evidence that we need to clean things to create a new foundation. But how this foundation could look like? Basically, we can take an example of piano arithmetics. So it's just a simple formalization of our ordinary math, right? So addition of numbers. It contains of a set of simple statements, axioms, so to say, which we don't need to prove. 0 is a natural number. There is an operation of equality between numbers. And after each number, there is another one. So there is a function called successor function, which evaluates what number comes after x here, like to the left, right? And to the right, we have a simple rule of addition. If we add 0 to some number, it's a number. If we add a number to some successor of another number, it's a successor. It is a successor of a sum. This is quite useless, you might think, but on the other hand, it creates some kind of strong mathematical foundation. We can mathematically reason about addition. So it's not like 1 + 1 = 2 because your teacher says so, or some smart guy like inferred it themselves. It is because we have this piano arithmetic, and we can actually prove the properties of addition. We can prove that 1 + 1 = 2, indeed. Wow. And Hilbert, he tried to apply the same reasoning, but to the entire field of mathematics, basically. So I guess I tried to visualize it like that. So in gray, we have axioms, the core ideas, which we don't need to prove at all. They are just like common knowledge. And rules of inference, which can take one statement and create another one. So as you can see here, we could have a core number of axioms for mathematics. Then we could infer other statements, true or false, and describe everything using this simple system. Wow, nice. Thank you, David Hilbert. And he didn't also propose that. He also proposed how to get rid of the paradoxes, some properties of such system. So the system needs to be consistent. What does consistent mean? So we have a lot of statements in the system, right? And we must prove only true or only false for every and each of them. So we can't have a statement which is both true and false, which is like described here graphically. Completeness of the system. We can't have a statement which is not connected to any other statements or axioms. Like for example, here I described it in yellow color. This shows a situation where a statement can't really be proven and it's not part of the system. So completeness means that we can't have such statements. And decidability. given such system, is there a way to construct an optimal algorithm which will answer yes or no statements? Basically, if this statement in green, is it like indeed true? Is it a part of the system? Decidability means that yes, and it provides some kind of algorithm that we can check in finite time and get an answer. That's three statements of the system which could solve every possible problem in mathematics described by David Hilbert. That was his work, his contribution. Then, after that, Kurt Gödel just rushed in and destroyed first properties. He said that the similar self-reference paradox could be applied in general to any kind of language, any kind of system. You can basically construct a statement. This statement is false. And he proved that we can convert the statement in such a way that it can destroy these two properties. So it means that no matter what we do, we still have paradoxes and we will basically suffer because of them. Because like our language is too powerful, it will have paradoxes. Mathematics is too powerful, yes. So we don't have consistency, we don't have completeness. What about decidability? Decidability, I'd say, is a grandfather for computing, for programming languages and all that we now know as information services, let's say, information technology, right? So these two guys, Alan Church and his student, Alan Turing, they decided to tackle this question by introducing some tools to create algorithms in mathematics. So we didn't have it before, right? We did have some intuitive knowledge. So they decided to formalize an ability to create algorithms, to compute stuff. So Alan Church, first of all, created a lambda calculus. Lambda calculus is just a new part of mathematical logic, mathematics, right? And it's very simple. It contains of variables x, of function definition. Lambda is a function definition basically. X is an argument, m is some kind of body. And it contains application. So we can apply function a to argument b. Also, it has two simple operations. First operation, it's like renaming, refactoring, right? If we have function that accepts argument a, we can rename it with argument x, and it doesn't really change the meaning of the function. So a squared, x squared, it doesn't really matter. And computation rule, better reduction, so to say. If we apply a function to some kind of argument, this argument replaces the input. So if we apply this function, which is squared to 10, 10 replaces the symbol x, and we can actually evaluate something. Wow, simple, cool. Thank you, Alan Church. Oops, where is it? Sorry, technical. Yes, problems. And the beauty of such simple and at the same time powerful concept is that we still don't tie ourselves to any kind of computational device. We use our mind, our imagination. We can evaluate expressions in any order at any time, and order of them, it doesn't really change. So at the same time, we get 25 as a result here, for instance. Very powerful concept, and yet simple. Turing, his student, at the same time, not at the same time, in fact, after the invention of lambda calculus, I guess, he invented Turing machine. It's an abstract mathematical device, which has some kind of internal state, and it operates on infinite tape, as you can see here to the left. So 0, 1, 0, 1, 0, 1, it's just some data on infinite tape, and infinitely goes to left and to right. And this Turing machine, it can read a value, write a value, and move its head to the left, to the right. The actions of the Turing machine are determined by its state, which is described to the right. So Q1, Q0, Q2, Q3, Q4, Q5, there are states. And the arrows depict some kind of changes. So based on the current value, how the state will change. Turing machine runs indefinitely or until it hits the whole state. It's a special state, which means that computation is done. We can relax and see our result, basically. So that's the core idea. Turing created a lot of theorems and theories and a lot of reasoning based on that machine. Basically, he created an Turing completeness, right? Equivalent of Turing machine and some kind of other system of manipulation. Turing proved that Turing machine is the most powerful computational device that can exist in math. So it will be nice to have some kind of comparison of other system of manipulation. Is it as powerful as Turing? So we have Turing completeness. So this equals sign basically. And it means if we can simulate Turing machine in that system of manipulation, we can say that they are equivalent. For example, lambda calculus is proven to be equivalent to Turing machine, thus it's Turing complete. So every theoretical work done by Alonzo George and Alan Turing, they kind of like describe the same, but using different languages. So they describe computations, but from different approaches. So to recap, yes, a lot of information. So, wow, my head is blown, literally. To the left, representation of lambda calculus, in my opinion, right? So we have basic functions, we can combine them, and then we apply some kind of evaluation. Evaluation basically just replace symbols. And at the end, we can see some kind of result of this equation. It's very abstract, order doesn't matter. It's very nice to have and to reason in. The Turing machine, on the other hand, is a device. It's not a language per se, right? So it's a device which operates sequentially, step by step. For example, it draws here a Nicolas Cage. It has some kind of internal state, and yes, it's not as abstract, and that's his entire point. It's a model of physical device. So what's about decidability again, right? So people created these two models. What about decidability property of the mathematics? Is there any hope? So Turing said, okay, let's have an abstract machine called halting machine. And as an input, it gets a source code of sorts of other Turing machines. So basically, it's a program that analyzes other programs. And the output of this halting machine is whether the input source code holds, so finishes, or it loops indefinitely and doesn't finish at all, no matter what. So basically, this program analyzes source code of other program and says if this program will finish or not. For example, if we pass while true statement, right, abstractly here, so if halting machine will return no, it doesn't hold. That's the idea. And what Turing did, he created a self-referential halting machine in the inversion of the output of the original halting machine and called it halting machine plus. And then he fed source codes of this halting machine plus to halting machine. Wow, he created a self-reference paradox. Halting machine holds when halting machine loops, and otherwise it loops when it holds. So contradiction, but the theory of decidability exploded. It was proved to be impossible. I guess David Hilbert would be quite sad. I'm not sure what was his reaction actually, but as a result of all this mathematical deep dive, what do we now know? That mathematics are still in shadows. We didn't formalize them. We still just learn to live with it. Gödel, with his incompleteness theorems, he created basically a shitstorm in linguistics, in theology, in philosophy, even in computer science. And our boys created the foundation of computer science, and now we have two models basic of computation. Wow, we have a lot of tools, and the whole world is in ruin. Nice, thank you. So Turing machine, as we saw, was a very good model of computation, and people start immediately adopting that. They created first computers. They tried to solve real-world problems. They automated work which was done by humans. They started getting profits, started getting some results, and it was a booming industry basically. And of course, profits were accumulating, right? And who wrote programs for such computers? It's basically some kind of tech priests, engineers, wizards, shamans at the same time, who knew the low-level language of a specific computer, who knew specific prayers to get this computer to work. And they basically just implemented some kind of business task as low-level CPU instruction and got results. So that was like the whole software development cycle there. Hardware became faster, better, stronger, everything was cool, everyone was happy, and we didn't improve that much, right? So we were happy, that's our peak. Actually, no. Such notion of programming was quite painful. We wrote a lot of low-level instructions, we lost track of the state, lost track of the programs, and it consisted more of the prayers, and it involved a lot of suffering. So people started to wonder, how do we improve our programming experience? Why do we suffer writing low-level code? So that's where development of programming languages begin, right? So logically in this presentation, not chronologically. So these languages, low-level languages focused on writing and getting value for business, I would call mainstream language. It's imperative, it has a lot of useful functions, for example, prints, logging, working with database, and it doesn't really care about mathematics at all. You just write stuff, like step by step. You send this stuff to customer, they pay you money, work is automated, everyone is happy, there is money, right? Cool. And in this diagram of usefulness, I try to capture this idea, how useful the language is. Like this language can really model business processes, you can implement some logic, you can do some computations, and you can interact with real world, consists of databases, operating system, network, other computers, and even users. Very nice, very useful. People started to wonder, how do we reduce complexity of our code? How do we reduce the amount of errors? And it boils down to the restrictions. Basically, assembler or binary punch cards, right? They are very powerful. Program is operating on bytes. For example, this dead beef, is it an integer, a symbol, and pointer? What does it mean? We don't really know, but it's like raw bytes and we use it in the program, and only programmer knows what that means. Then we had typed languages. We had primitive pointers and different user-defined structures. So we kind of limited what can be written and what can be read from some specific point in memory. And typed but cooler, I'd say it's like additional infrastructure around typing. So generics, more type checks, more elegant type constructions, custom types. I guess that's where evolution takes us. So more restrictions and less cognitive overload. I tried to depict the cognitive overload using these pictures for like visibility, right? And the same happened not only for data, but also for logic and computation itself. So we had assembler. It can go to basically anywhere. The execution jumps from one point in memory to another. And it's quite hard, like spaghetti code, right? Then we invented structured programming. We reduced the power of goto to a specific if then else, branching operator, for and while loop operator, and others. I'm not sure if I recall any of them. I guess that's the whole set, right? And after that, we said, okay, but we need more. We need to reuse code more. I don't want to write the same code my colleague used. And we need to create some kind of boundaries between them. So people invented object-oriented programming. You can't just go to anywhere. You need to implement a interface, inherit some method, overload the virtual method, call some function. That's a lot of barriers to overcome, right? Instead of just go to some specific address in memory. And I only mentioned like typed languages, but that's only my preference. Dynamically typed languages have special place in my heart, and I don't really like them, to be frank. So I won't mention them anymore. And let's take a look back. Now, here we have a plot of how language is useless and useful, vertically, and unsafe and safe horizontally. So usefulness we already discussed, right? How we can interact with real world and solve real world problems. Safety refers to the power and number of abstractions that limit us, and we can't write just bad code. So that's what safety means here. So mainstream languages go to this utopic and ideal domain of safe and useful languages by absorbing some kind of good stuff from everywhere. They absorb notions from some academic paper, they absorb notions from within the same group, they just invent new stuff basically. So that's plan A, this movement horizontal to the right. And people rejoiced at last. Object-oriented programming, structured programming, they gave the results. We suffer now less. We are focused on delivering value and writing good code. But there is still something like prayers are still there, and we still don't quite understand what's happening in our systems. And sometimes there are edge cases which are hard to implement with structured and object-oriented programming. And if we look deeper into the map of influence, so to say, of different languages, we can see here there's a group of languages derived from lambda calculus, and there's a group of languages derived from Turing machine. They interact with each other, they share some ideas, some notions, and they basically evolve. That's the process that I described before, right? This horizontal plan A. But we didn't really discuss the functional category of languages. The languages derived from lambda calculus. What are they? They are basically languages that implement lambda calculus in some sort, or some kind of any other type of mathematical logic. Or like just in wide definition, it's just a programming language that doesn't really care about you, about your computer. It's just created by academics for fun. Yeah, that's the rough truth. What are the processes inside functional programming languages? So we already discussed that they are purely for academic problems, right? For playground for research, and they are actually quite heavily inspired by papers. So some of the languages don't even exist as binary for our computers. They're purely implemented on paper. For example, that was Lisp. It was created only on paper. Type lambda calculus, sorry. It's just an extension which adds some type information into our lambdas. Then people started wondering, okay, object-oriented programming has inheritance. Structured programming has structures. How do we model that? They created type theory. So it's algebraic data types, pattern matching, polyformism, type inference, which is all basically founded on some kind of mathematics. So it's not only like QWERTY compiler or language developer that does that, it's mathematically proven concept. Type theory, thank you, I love you very much. Category theory, very hard, a lot of scary words like monad, functor, and scary symbols. Let's just skip that a bit, but it's also a powerful and very useful concept. So as we know, functional programming, was it really useful? Yes, for academic purposes again, but no, because you can't really implement real stuff that interacts with database. Why? Because developers didn't really care. Again, as I mentioned, Lisp developers created Lisp only for paper purposes, as an experimenting with how computation can be expressed. And they just accidentally implemented a compiler for that language. And well, we now have Lisp. That's the first problem. The second problem is that functional programming, being mathematically dependent, right, can't really handle side effects. For example, we have a function here, square. It takes an input of integer and returns integer. And it basically calculates a square value of some integer. It's pure, simple mathematical function. But again, we also use print function. It takes any kind of data structure, it returns nothing, but it does send bytes, strings to some kind of global or operating system handler and shows information on display. And also, without even operating system, there could be, like, for example, string builder class, right? Which, as a side effect, populates internal state. So you give strings there, and the strings are collected inside of, like, internal variable, for example. So all these things in gray that I showed here, they are side effects. Things which are not expressed by inputs or outputs of a function. And because we didn't have tools to handle such kind of methods, we can't really interact with real world. So write to DB, log, send async with some callback, right? Or get popular item from DB. They could be useful functions. We could use them, but we just can't. Assume that there is, like, an import somewhere, which, like, defines function print, which returns nothing void and takes in anything. And function square, like the same semantics. And let's look at this snippet of code. Let A, B, C equal some statements in A equals SQR. So A, B, C is just a synonym for these executions. We can do them step by step if that's easier for you to understand. The semantics doesn't really, like, matter or care about the execution. What we care about is that compiler, being mathematically pure, can say that since print returns void every time, we can just replace the call of the function with void. Like, technically it makes sense by the types, right? And it can create further optimization and reduce our whole problem into one single statement true. But at the same time, we lose the necessary side effects which could bring value to our business, for example. Instead of print A, we could say use write to database, and our program magically doesn't write anything anywhere. So that's the huge problem which was, like, plaguing the entire domain of functional programming. Or, for example, another example. So there is a function get popular item from DB. Assume that we call it twice, but with pause of 7 days or 1 day. It doesn't matter. There is some kind of pause between these calls. Is this assertion true or false? Will it fail or will it not? How compiler can optimize this code? In C, for example, or mainstream languages, compiler is quite pessimistic about such optimizations. He won't touch it. I hope that he won't touch it. But in functional programming languages, compiler, being mathematically pure, reasons about function by types, and he can just alias and make this assertion true. He won't just, like, call the second time this method, and assertion will not fail. And it will, I guess, break the semantics that we put into this piece of code. And all this usefulness is gone, basically. So we have a world of pure fantasies where we can describe business processes, computations, and logic using high-level abstractions and latest mathematical developments, but we can't really interact with real world. That's useless. That's very sad. So I guess there's another view, right? How we can put functional languages into our mental map of the languages. So yes, it's safe, very safe, in fact, but it's useless. And people started to take a notice of that, and they wanted to improve that. So they started thinking about how we can encode the side effects into the functions. So to say functional effects. So they are no longer side effects. The effects because they are encoded somehow in the type. How did you do that? Enter plan B implementation. It's IOMonad implemented in Haskell by accident. There is a great talk by developers of Haskell, how it was, like, literally discovered by accident by some researcher that we can actually encode side effects using this high-level abstraction. But let's not dive deep into that concept. I will just say that it just provides a general interface for such data types as future, list, optional, observable, stream, mono, flux. They're all data types which are generic, right? They are wrappers, so to say. And the old way of using them was carefully reading documentation and source code in order to work with them and understand their methods, etc., etc., etc. What Plan B and category theory and AO Manat says is that you can just have predefined set of methods here, flat map, map, and pure, and use universally for any kind of such data type. So if you want to create a new thingy from the old thingy, you use flat map function. If you want to change value in given thingy, you use map. If you want to create a new thingy from scratch, you just use pure function. And the compiler will make sure everything works by magic. Yes, magic. And what are benefits of such paradigm? What is the benefit of category theory for us, for programmers? Not talking about this abstract data types, right? So I guess all of us encounter callback hell when you pass function into function into function in order to handle some kind of nested results. Category theory and this unified interface gives us ability to convert this callback hell into declarative execution, step by step. You just write results from A, B, C, D, and you use them declaratively and sequentially. It's easier to understand, and I guess it's a nice way to show how mathematics can help us chain our computation, right? So make it better to understand and maintain. So overall, to recap, why people are interested in functional programming? Because it's safe and elegant concurrency and parallelism. So it provides a lot of mathematical abstractions, wrappers. So you don't just use semaphores everywhere, or you just use callbacks. You use functional data types that help you create safer code. They have powerful type systems. They all, at the same time, have lazy, but at the same time, powerful optimizations. Combined, it makes compiler a very strong tool in the hands of the programmer. And also, functional programming utilizes a lot of cutting-edge concepts from academic research. So, functional programming, I personally would say, it tries to implement the idea if program compiles, therefore it works perfectly, and it gives you basically tools to do that. Another problem with plan A, so a little detour here, right? So we discussed plan A, plan B. Problems with plan A and staying with the same mainstream languages is that they, for example, have the option in notion of null. Null, by null, we mean that some reference or some value, it doesn't really exist, absence of value encoded. In functional programming languages, we don't simply have nulls. We need to encode it somehow explicitly. For example, there's a data type called maybe. If you are familiar with concept of enumeration, read it as there's an enumeration maybe with generic type A, and it can have two options, just A, which contains some value, and nothing, contains nothing. Java saw that interesting concept, and I guess in streaming API, but I'm not sure, it adopted this approach, right? So there's optional interface, if I'm not mistaken, or active class. And in Java, you can just write optimal foo equals none instead of null. Wow, Java, thank you very much. You made yourself better, right? By getting rid of the $1 billion mistake, this null, nasty stuff. But at the same time, the huge legacy of the Java and like this idea to appease both sides of the programmers, it created just another layer of complexity. For example, this is a very nasty result, very nasty example. So we have like Boolean, which could be valid true or false. Then, of course, Boolean is reference type and optional is reference type. So we can have nulls. And optional empty is another way to encode the absence of value. So it creates a massive overhead. People just, I guess it scares them when they encounter such misuse. And it creates this negative image of the functional programming concepts. Like if a person coded that and didn't really understand the notion of optional, they would just say it's a useless concept, right? So it's, I guess, very bad to just stay within the same scope, within the same context. of the language. So this problem it is an example of many other problems that we have with mainstream languages, with legacy. And I guess, in my perception, it creates some kind of envy towards functional languages, where everything is pony and rainbows and utopic and ideal, and you can just you just don't care about nulls in your code. You just write beautiful excellent code that compiles for 100% of time. Nice, cool, right? So yes, this kind of like arrow, yes, I want to describe that feeling towards something more beautiful, let's say. Whew, that's a lot to have. So yes, the this slide, I guess, exactly demonstrates how I view programming languages, how I feel about them. And I guess the result of the presentation is here. Like, presentation served its purpose. As Mr. Morgan Freeman says, we are at the end. And I guess I wanted to conclude this presentation with some key points, right? Which I discovered for myself while I was investigating everything related to this topic. So first of all, math is a symbolic language. Functional programming is trying as hard as possible to use math to solve computational problems. And functional programming was useless academic tool until functional effects. So I understand why there is some kind of bias toward that, or against that. For myself, I say that I need to constantly search for better tools to do my work. I really enjoy writing functional code, and I want to improve myself. And I don't want to be a slave of old ways. Java, I personally don't like it. I just wanted also to give special thanks for people who helped me create this presentation, who helped me formalize my thoughts, right? And supported me all the way. Thank you very much. I hope that wasn't confusing at all.
Thank you so much for the presentation. I think everybody enjoyed it quite a lot. And I'd like to ask if anybody has any questions to ask. Maybe you could use a chat if you are not comfortable asking them. All right. Or maybe this topic was so fulfilling that no questions.
Yeah, I was hoping for opposite reaction, to be frank. I tried to create some kind of controversy, right, with a holy war.
Yeah,
I guess our engineers are way too smart for that. Yeah, they are not as easily triggered by stupid statements that I used.
Thanks, Bulat. Very interesting presentation. So you really think that functional programming in its current form is useless?
Well, I guess it was useless, but nowadays I discovered that there are more and more tools to make it useful, and I do so practically. So I used it with Konstantin in Hydersphere project, and I use it now in Crystal project. And I feel like some problems are solved much beautifully, right? And there are way more guarantees from compiler. So I really believe that it's not ready for wide adoption, but it's getting there.
It would be interesting to hear in which cases you used functional programming in real projects.
Oh, okay. Yeah, we can also discuss that, but I guess it's a topic for another presentation about how functional programming has its own practical tools, and we can use some kind of maybe simpler use cases, right? So maybe a demonstration of them would help. I'm not sure. I'm still thinking about that, but that's a good idea. Thank you.
Yeah, would love to hear that. From my opinion, one thing that impedes more widespread adoption of functional languages, it's their power. So its expressiveness. They are very, very expressive, and you actually can write very concise statement that expresses a lot. So it's a lot of enjoyment when you are able to write this way, but there is like another side of it. It takes an effort to read and interpret it. So you cannot read it like a poem and get everything. So you have to think, to infer, to understand what the code does.
Yeah. Well, I guess the answer to that problem is that, as I mentioned before, right, FP was a tool for only academic purposes, majorly for academic purposes. And academics, they use this expressiveness to put as much as information and computation in as less symbols. It's powerful, it's nice to have, and you feel accomplishment, right, when you write it and you feel that you understood it. But at the same time, I guess it takes discipline to write maintainable code. So I guess it's a maturity problem for FP. As like we discussed before, there was like interaction with real world. I guess another factor of maturity for FP, it's code styles, linters, etc., things that will help us not only write abstract and one-line code, but also comprehensible for other people. And I guess, judging by my experience with Scala language, people are getting there. So they are already tools that can enforce you to follow some kind of like style guide. I can't say for sure about Haskell though. Maybe they still suffer from that. But still, right? So if academics will only use that languages and harness the power of FP, and engineers will be scared because someone can write one-liner, who will improve FP? Like, I guess it's kind of like our responsibility to be more open-minded, right, to this bleeding-edge technology. Like, for instance, Provectus focuses on email, which is itself bleeding edge. Why don't we improve, for example, programming languages, programming experience in that way? That was my thought basically for the last month. Quite philosophical one. So yeah.
Yeah, I suppose there is like a barrier in count of people that are using some technology. While it's a low number, the wider public is scary to try anything like that.
That's true. Yeah. So and I guess that's one of the goals of my presentation, like to show people that it's not as scary. Well, yes, it's quite confusing because it's like kind of alien. You are not used to this concept, for example. I wasn't used to this concept. It was quite mind-shattering experience for me. But I guess we still need some kind of practice leaders, right? So who will drive others and teach people how to not to be better, but know more, for example, right? To choose proper tools, to feel more safe with experimenting stuff, knowing that there are people who know, who can maybe help you with some expertise. So yeah, I just wanted to maybe to address these questions. Maybe. So, yeah, I lost track of my thoughts. Sorry. Quite exciting.
What do you think? Would it be interesting to do some practical lecture on some of actual FP languages?
Well, it's a nice idea, but I'm not confident in my competence, so to say. So I am free to suggestions. We could arrange some kind of like collaborative problem solving using FP, right? But I don't think I qualify as a lecturer, to be frank. I'm still like a novice here.
You actually gave very, very deep mathematical foundation for everything you told. So you are a good lecturer.
No, thank you.
Yeah, I can agree definitely that it was a wonderful presentation. All right. Maybe any other questions or suggestions or points for the discussion? All right. Well,
Yeah,
in this case, oh,
I'd like to add that in general the presentation was really cool, and these memes really helped a lot to be attached to all this hard stuff with math and the story of programming in general. So I'd like just to say thank you very much. It was really interesting.
Thank you for kind words.
all right. Well, on this positive note, thank you so much, everybody, for coming for this demo session. Thank you so much, Bulat, for preparing such a wonderful presentation, and have a wonderful rest of your day. This video would be available soon for your usage. All right. Have a great day, everyone.
Yeah, thank you, everyone.